Picture a simple weight bouncing on a spring. Eventually, friction takes over, the bouncing slows, and the weight comes to a complete, dead stop. But if you shrink that system down to the atomic scale, the rules change. A quantum particle never reaches a state of absolute rest. To understand why, we start with the classical model. Looking at this vertical spring apparatus, we know from Hooke's law that the restoring force is proportional to displacement. This gives us our classical potential energy formula, 1/2 kx squared. We take that classical potential energy function and plug it directly into the time-independent Schrödinger wave equation, replacing the v of x variable. Because a perfectly still particle violates the uncertainty principle, we must now solve this equation to prove mathematically why a minimum level of motion is a physical requirement. This second-order differential equation is cluttered with physical constants: mass, the spring constant, and Planck's constant. We clean it up by introducing a dimensionless variable q and grouping the remaining constants into a new energy parameter lambda. This yields a simplified dimensionless differential equation. To solve this, we look at the extreme edges of the system. What happens to the wave function at massive distances from the center as q approaches infinity? At these limits, the q-squared term grows so large that it completely overshadows our energy parameter lambda. We can safely drop lambda from the equation. This chart shows the two mathematical solutions to this asymptotic equation, a positive exponential and a negative exponential curve. The positive curve grows infinitely large at the edges, which would result in an impossible infinite probability density. We must exclude this result, keeping only the negative decaying curve. The physical requirement of a confined particle forces us to filter out mathematical solutions that do not result in a finite probability. We now propose a complete solution. We multiply our safe, decaying exponential by an unknown polynomial function, h of q. Substituting this back into the Schrödinger equation gives us the Hermite Differential Equation, which we solve using an infinite power series expansion. Let's look closely at the sums. By shifting the index of the first summation by r plus 2, we match the powers of q across the entire equation. This allows us to cleanly isolate the recursion formula for the coefficient a sub r plus 2. If we let this recursion series run infinitely, the ratio of successive coefficients behaves exactly like the positive exponential curve we already rejected. The entire wave function would diverge at the boundaries. To maintain a finite wave function, we must force the series to terminate into a finite polynomial. This is achieved by setting the numerator of our recursion relation exactly to 0. This act of truncation, cutting off the infinite series to keep the wave function bounded, is the mechanism that restricts the system to specific, allowed energy states. Setting the numerator to 0 yields lambda equals 2n plus 1. Substituting this gives the quantized energy, E sub n. Inside the parabolic potential, these discrete energy levels form equally spaced horizontal lines. Here, Hermite polynomials define the wave function's probability shape. In the lowest state, where n equals 0, the energy is 1/2 h bar omega. This is the 0-point energy. It confirms that because of the Heisenberg uncertainty principle, a confined particle can never reach 0 energy and must always maintain a state of motion. By inserting a classical spring potential into the Schrödinger equation and truncating the series to preserve a finite wave function, we prove that the oscillator exists in discrete energy steps, with a ground state that can never be at rest. Picture a simple weight bouncing on a spring.